We're going to look at the idea of finding the area underneath a curve, which is also known as a definite integral, which is sometimes referred to as just an integral. Now on the left over here, we have the shaded region underneath our curve that's all represented, but we'd need to figure out that area. Back in the first two packets that we completed, we actually used rectangles to estimate the area underneath your curve. And we noticed that as we did more and more rectangles, we got a better and better estimate of what was going on. And here we see in several pictures that as you do more and more rectangles, that you become or get closer and closer to the actual area. You'll notice up here in our areas underneath the curve, you have these relatively large, almost triangles. Here you have relatively large, almost triangles above. Here they weren't being counted. But you'll notice when you get down here, all that extra on the blue or all that white space on the pink ends up getting a lot smaller. So therefore your error is less as you do more rectangles, or you can say you have a more accurate answer as you do more rectangles. So go ahead and let's look at the last problem, which was y is equal to an x squared. So put that in your calculator. We're going to use 10 rectangles, and we were looking at our area from 0 to 3 on those last pictures. So put the y equals x squared in your calculator, into the y equals. Run your program that allowed you to figure out the area underneath your curve. And then you'll end up getting this for your right endpoint, this for your left endpoint, and if you average those two, you get your trapezoid. Now, to find the area underneath your curve from 0 to 3 of your function x squared with respect to x, we would write using calculus as this notation right here. And we were estimating that with our calculator. However, we will look at a little bit later here how to find the actual answer, the exact answer, rather than just the estimate. But we need to first of all review the idea of summation notation. We talked about this in our first packet. When you have several terms added together, you could write it just as your rule here with your summation notation in front and your indice in the bottom telling you what to start at, and your indice in the top telling you what to stop at. So if we want to evaluate these down below here, here's your rule in the parentheses. So to get your first term, you got to take what you start out with here, which is 1, plug it into your rule, plug in 1, add 1, you get 1. Then you got to go plus. Plus because it's a sum, because that's your summation notation. You plug in the next number above 1, which is 2, plug in 2, add 1, you get 3. And you keep doing that until you end up plugging in your last number, which is 7. And then you just want to go ahead and add those together. And when you add those together using your head or your calculator, you end up getting 35. Same approach on this one over here. Your rule is 2 to that power, so you plug in 1, 2 to the first. Then you got to go plus. Plug in the next number up, which is 2, you go 2 squared, plus, plug in the next number up, which is 3, 2 to the third, and you keep doing that until you end up plugging a 6 in for your n. And then you just want to go ahead and either type that into your calculator or work it out in your head to get your sum. Here we have some rules in dealing with summation notation. Now, our C right here is referred to as a constant. Basically, it's saying, well, if you have a constant, just pull your constant here out in front, and that's what we're doing. So if you have a constant times your function, pull your constant in front. On the next one down here, all we're really doing is We're just saying, well, let's go ahead and distribute your summation through to each one of these. And that's what we're doing to get this over here. So instead of just adding two things together and then figuring out the answer and then doing your sum after that, it says do the sum of the first one, sum of the second one, and then add those two together. The bottom one here says 1 added together n times is just n. On the far right over here we have some rules. If you have the sum of I added together n times, gives you this one here or this one here. There's two rules to choose from. For the most part, if you know the value of n, you want to use the first equation or formula. If you don't know the value of n because it's going off towards infinity, then you'd want to use the second one. And that's more or less true with all these. If you know the value of n, use the first single fraction. If you don't know the value of n, then you want to go ahead and use the second one. So the next one down is the sum of an x squared. There's two different options there. And the bottom one down is your sum of an I cubed. And there's two options there for you. So let's go ahead and use those formulas to work out the answer for this sum. Well, here we can apply our sum to each one of these. We can distribute that through. That's what we did on our first step. But you notice after your sum you have a number, which is your constant. You can pull that 7 out in front. You could pull that 5 out in front of your sum. So you pull your 7 out in front and you will get this. Here you put your 5 out in front and you will get this. You now have a formula for the sum of an I squared. That formula for the sum of an I squared is given to you over here. Since we know what n is, notice n's what's on top of your summation, which is 10, we're going to use the first formula. Here we have the sum of an I, so we're going to use that formula right here. And then once again, since we know what n is, we'll use the first formula. So all we're going to do is just plug those in. Your 7, and then your formula right here, with n being 10 being plugged in, and 7, and then that formula simplifies a little bit. Then we're going to look at after the subtraction sign here. We know it would be a 5, and then we're going to use our formula for the sum of an I. Formula for the sum of the I, plugging in 10 for your n's. We get this. Your parentheses simplifies a little bit. You could reduce each fraction if you wanted to, or just type it all into your calculator, and you end up getting 2,420. On this one here, we're asked to take our limit, but you'll notice on top we have a sum. So we're going to go ahead and rewrite that top, which is a sum, in summation notation, which we would have as this. Now we have a formula for this. So we're going to plug that in. Since we don't know what n is, we'll use the second formula for that. We get this here. One big fraction here, so I'm going to rewrite it, taking the first one over your denominator, and then taking the second one over your denominator. Then you can go ahead and reduce each fraction. The n squareds drop there. Here you'd have a half, an n over an n squared leaves you an extra n on the bottom. Now as n gets really, really big, it has no effect on the half. And as n gets really, really big here, it causes the second one to go to 0 because it's 1 over something very big. So it's 0 plus that.